So here's the third formula we want to solve. Okay, we're solving for g in the formula p equals square root of KL over g. This is an actual formula that you'll run into in physics. Okay, it describes how long it takes a pendulum to make one oscillation. Okay, so this is the period of a pendulum. But it doesn't matter, we're just going to solve it for g. Okay, so the first thing I would do, since I'm solving for g, is get rid of this square root, right? G is trapped inside this square root. I cannot move anything inside here until I get rid of the square root. So the strategy for getting rid of a square root is to square both sides. So let me start with that. So in my formula, I'm going to apply a square to both sides. The square and the square root are going to reduce or cancel on the right side, leaving me with p squared equals KL over g. Now, to get rid of this denominator, I'm going to have to multiply both sides by the LCD. In this case, the LCD is just g. It's the only denominator. So my next step is to multiply both sides by g, which gets rid of the g in the denominator and brings it up on the other side. So now I'm at g p squared equals KL. Finally, if I remember that I'm solving for g, I need to get rid of this p squared, which is attached by multiplication. So to get rid of multiplication by p squared, I divide by p squared. So these reduce away, and I'm left with g isolated. So I've solved the formula for g. G is equal to KL divided by p squared. Okay, so in this formula we noticed that we had a square root trapping the g, which we were trying to solve for. So we squared both sides. Unfortunately, that left us with a denominator, so we multiplied to get rid of the denominator. And then finally, we were able to divide by p squared to get g all by itself. Alright, so here's our last part for example 1. We have a new formula, s equals 4 pi r squared. And this is again an actual formula you might run into. It describes the surface area of a sphere. Right? But it doesn't really matter right now. Right now we're focusing on solving this formula for r. So when you analyze this formula and you recognize you're solving for r, your brain should think, oh, well, my variable is squared, right? The r is squared. So in order to solve a formula for a variable that's squared, you're going to have to isolate the squared variable and then use the square root property. Okay, so let's isolate the r squared and then square root both sides. Now, if we're trying to isolate the r squared in this formula, we have to realize that the 4 pi is connected by multiplication. So in order to move the 4 pi away from the r squared, we have to divide both sides by 4 pi. All right. So that's going to get rid of the 4 pi here and bring it onto the other side. Now, you might be concerned that we've introduced a denominator into our formula by dividing by this 4 pi. But don't worry about it because the denominator doesn't have the variable. Right? There's no r in this 4 pi, so it doesn't really bother us. Right? Let's write what we're left with and continue solving for r. So at this point, because I have my r squared isolated, I can get rid of the square by square rooting both sides. This is what the square root property tells us. The only catch is, when I eliminate the square and the square root, I have to put a plus or minus on the other side. So we're left with r is equal to plus or minus the square root of s over 4 pi. Now, r is isolated at this point, okay? But let me make two quick notes. First, about the plus or minus. You need to watch the instructions. Okay, even though we end up with a plus or minus here, if the instructions say to only include positive answers, then you would drop the negative portion. Right? For example, I know, and I told you, that this is the formula for the surface area of a sphere. And the r represents radius. So if I know that r is supposed to represent radius, I'm not going to worry about the negative portion because the radius of a sphere is never negative. However, there were no instructions here that said I should drop the negative. So I am going to go ahead and leave it in. Right? The second note I wanted to make is that we can simplify the square root of s over 4 pi. Right? So let me work with this quantity here, this expression, and try to simplify. One thing you should always try to do when you have a square root of a fraction is take the square root of the top and the square root of the bottom in hopes to simplify. So I'm going to rewrite this equation as r equals plus or minus the square root of s over the square root of 4 pi. And in fact, I know the square root of 4, right? And since the 4 is connected by multiplication, I can take the square root of 4 outside of the radical. So I'm going to rewrite my expression again. And the right side is going to become plus or minus the square root of s over 2 root pi. Finally, we don't particularly care for square roots in the denominator, so I'm going to go ahead and get rid of that square root by rationalizing the denominator. You do this by multiplying top and bottom by root pi. So what happens, on the top, you end up with root s times root pi, which is root s pi. So plus or minus root s pi. And then on the bottom, the 2 stays, and root pi times root pi is root pi squared. And then we know that when you square root a square, you can cancel them out, and we're just left with pi. So I'm going to put pi on the bottom. So that's my solution for r. It's equal to plus or minus the square root of s pi divided by 2 pi. So as a brief recap, how did we handle this formula? Well, we were solving for r. We saw that r was squared, so we isolated the squared quantity, and then we square rooted both sides, remembering that when you square root both sides, you get a plus or minus. Of course, if the instructions say that you only want positive answers, then you should rule out the minus. Right? But we didn't have any special instructions, so we kept the plus or minus. But we had to focus on simplifying the radical. So we took the square root of the top, square root of the bottom, and then rationalized the denominator. And now this is our solution.